Well, thank you everybody for coming. Hello, good morning, good afternoon, good evening, wherever you're joining us from today. Thank you so much for coming, and welcome to the Revolutionizing EEG webinar series hosted by your friends at Wearable Sensing. We're really excited to be launching this new webinar series where we're going to explore the many exciting ways in which researchers are using advanced dry EEG systems to bring their research out of the fixed lab environment and into the real world, in order to study the brain in more dynamic and ecologically relevant contexts. So with each episode, you'll learn about all the benefits and challenges of doing real-world EEG research, as well as what kind of insights we can gain from studying the brain in these naturalistic contexts. To kick off this series, we couldn't imagine a better example of real-world EEG research than the work of Dr. Adi Korisky. Dr. Korisky is a cognitive neuroscience researcher at the Stanford Graduate School of Education, where she studies attention and learning in real-world environments under the mentorship of Bruce McCandless. Her work focuses on advancing individual-level neuroscience using mobile EEG, with an emphasis on naturalistic settings such as classrooms. Adi has developed innovative paradigms that combine collaborative work with teachers and students, ecological stimuli, and portable neurotechnology to better understand how attention operates in everyday learning contexts. Her current efforts also focus on creating research centers that bridge neuroscience and education, aiming to extend the scientific insights into authentic learning environments. Her work has been supported by competitive scholarships and fellowships, recognizing both academic excellence and translational impact. All right, so one last thing before we get started, just a quick mention that we would really love to hear from all of you that are attending today. So please make sure to drop your questions in the Zoom Q&A below, and we'll flag them for our Q&A discussion in the last approximately 15 minutes. So with that said, thanks so much for joining us, Adi, and I'll hand it off to you.
Yes, thank you so much. Thank you for having me here. I'm super excited to be here and open this wonderful webinar series of Revolutionizing EEG. And thank you everyone for coming today. I'm going to share my slides now. And we can start. Okay, so today, as you just mentioned, Ryan, we are going to talk about attention in classroom, or to be more specific, I'm going to present to you today a bidirectional approach for studying attention in authentic learning environment. And we are going to do it by building a bridge from the lab to the classroom and back to the lab that allowed us to understand what's happening in the brain of the students when they're sitting in the classroom and try to listening to the teacher in real learning, authentic environment. And let's start with talking about attention and education and why is it important. And the answer for that is that to be able to learn something in the classroom, you need to control your attention. You need to use it every minute of the day. Students that sit in the classroom listening to their teacher can use their attention to focus on what matters throughout the class, which meaning listen to their teacher. They needed to integrate multiple meaningful sensory streams. So you can imagine a student that sit in the classroom, try to pay attention to their teacher, but the teacher is also using presentation or visual aids, or they have a worksheet in front of them. The students need to divide their attention. They need to select what they want to pay attention to, and they need to integrate this information together. And also, we need our attention to resist competing external and internal distraction. As we all know, the classroom is noisy, the classroom is messy. When you are sitting in a classroom, it is possible that your friend talked next to you, or that you might even remember things that you should have done but forgot to do. And all of this can draw our attention from the teacher. And if we're thinking about attention through this lens, we can think maybe about attention as a superpower that the students have. And students that are able to control this superpower, that are able to control their attention, could be a better learner compared to students that more struggle with controlling their attention. Now, with this phrasing, we can ask all kinds of questions. If we have kids that are better in controlling their attention, that are better in controlling or take agency on this superpower, is it possible for us to identify neural mechanism that allow us to know which one of the kids will show better control on their attention? And if so, can we identify can this neural marker be associated to better learning outcome in the classroom? Can we say something from the brain of the kids about what's really going to happen in the classroom? What are going to be their learning outcomes? And I wish that I have a simple answer for that, but the answer, as most of the thing in life, is that it's complicated. And when we are going to the literature on attention, more and more recent studies suggesting that there is a translational gap between the things that we are measuring in the lab and the way we interpreted or predicting real life learning in classroom. And despite decades of studying attention in the lab, and I'm a cognitive neuroscientist, I study attention. There is a lot of things that we do know about attention in the brain, about the neural mechanism of attention. But when we're trying to take all of this evidence and say something about real learning, we see that traditional lab paradigms fail to predict how attention fluctuates during real life, how it varies across individual learners. And the most important thing for me was how it relates to authentic learning outcome. And as I mentioned, more and more studies are showing that in the scope of attention, but this translational gap is actually a bigger question in the world of neuroscience, pointing about the differences between studies that conducted in the lab and studies that are happening outside. In the real world. On one side of the spectrum, we have lab-based studies. These are the classical studies where we ask, and again, I'm going to talk about the scope of attention in our education. So imagine that in this part of the spectrum, we are asking students or kids to come to the university, sit in front of a computer in an isolated room, do a battery of cognitive tasks. These kind of studies have maximum control. We can control all the variable. We know exactly what we are measuring. It's much more easier for us to interpret the neural signal. But on the other hand, it's very different from what's happened to these kids when they are in their classroom with 20 of their peers listening to their teacher or different teacher, different topics. And this is why in the recent years, more and more studies are started to move toward naturalistic environment. And thanks to the technological advancement that we have right now, we are able to take mobile EEG devices or FNIRS, put it on kids' head and send them to walk in the world and see what's happening in the brain. Or at least this is the title. But for those who work with naturalistic environment, we know that it's more complicated than that. Even when we are able to get a good quality signal, which is not that obvious, it's hard to interpret exactly what we are seeing. It's hard to understand what the brain is telling us when the kids in this multiple, noisy, with all this variable environment. And this is why today we are going to talk about a bridge, a bidirectional approach that allow us to create a more relevant research, a science that is more related to what's really happening in the classroom. And I'm saying that to do that, to be able to create relevant science, we must develop new experiments that bridge the lab and the classroom and allow us to get the pros from each one of these methods and combine it together to something new that we wouldn't be able to achieve by looking only on one of these contexts. And I'm also suggesting that we shouldn't do it by ourselves. If we're trying to create relevant science, if we want to understand what is happening in the classroom, we need to work with people that really understand what's happening in the classroom. I'm a cognitive neuroscience. I know a lot about attention. I don't know a lot about what is happening inside of a classroom and how attention is looking in the classroom. But educators and teachers and clinicians and even students do know. In this specific project, I'm going to emphasize how working with educators can help us do a better and more relevant science because teachers got a deep knowledge on students' ability. They know what engage the student, they know what challenge the student, and the most important thing, they got their own superpower of looking at a student or looking at a group of students and know if they're paying attention or not. And with all of that, let's talk about the goal of this project. So the first goal was to develop translational paradigm that measure attentional dynamics across lab and classroom, something that would be relevant to both of the environment. The second goal was to identify neural mechanism that underlying individual differences in classroom attention. So we created a paradigm. Now let's talk about the brain and how we can identify the neural mechanism within it that can help us identify this superpower or the controllability that I talked about. And last but not least, we want to link all of these measurements to authentic learning outcomes and see how it looks and how attention is operated in an educational environment. And to do all of that, this is the what. Now let's talk how we can take this goal and make sure that we really do it in the wild, in school. And to do that, I was so lucky to work inside of the Brainwave Learning Center, or the BLC. This is an amazing initiative. I'm always smiling when I'm talking about it. That was established by Bruce McCandless, my advisor. It's in a school, which is a K-8 school at Menlo Park, California. And the BLC is a center that sits inside of the school. Inside of this center, there are neuroscientists that just work in the school every day. And this is an amazing environment because the goal of this study is to working with students, working with teacher, and better understand what are the questions that emerge from the field and how we can use neuroscience to give them some answers. For me, this was perfect because it helped me to work with teacher, but also to sit inside of a school every day, talk with students, and see their day-to-day lives. And inside of the BLC, I conducted 2 studies. And this is what I'm going to present to you today. So the first study is one direction of the bridge from the class to the lab. Here we try to identify individual level neural mechanisms of attentional control based on teacher-informed insight. So here we use traditional EEG devices. We were in the lab, but we use insights from teacher to better understand what are we seeing in the brain. And then we moved to the second study, which was the other direction, from the lab to the class. And here we wanted to know how lab-based attentional patterns, or the patterns that we identified in study 1, manifest in authentic learning environments, which mean in the classroom. And here we use the mobile EEG devices. So you do need to survive a few slides before we're going to talk about the mobile EEG itself. Let's start with study 1. So study 1, from the class to the lab. The goal is to identify individual level neural mechanism of attentional control based on teacher-informed insight. And for that, I was so lucky to work with the teacher of the student, Miss Shelley Whitted. Shelley is teaching the kids social studies. She teaches a 5th and 6th grade student, which were the cohort of both of these studies. And she know the kids by heart. Some of them she knew for 2 years, other for 1 year, but she's well familiar with them. And Shelley was part of the designing of this study every step of the way. Together we created the text within it. We decided on the parameters. We wanted to make sure that whatever we design, whatever we ask the kids to do, will be relevant and relate to what's really happening in their classroom. And remember, we are trying to create this bridge. So this is one of the stones in there. We want to create something that can really speak to the kids. And when they're doing it, they feel like they are in their classroom. Another thing that is important to mention about this study is related to this picture. So what you're seeing here is one of our students. They are sitting with a traditional EEG net on their head, and it looks like almost every EEG lab in the world, but this one is a school-based EEG lab. So this lab is located inside of a regular classroom, inside of the school. It is part of the school life. The kids are familiar with this room. All the kids know about EEG because the amazing team of the BLC talked with them about it. And this specific class is located few steps from the student regular classes. So again, we are in this study, we are focusing on the lab, but we are trying to put inside all kind of small feature that make it more natural and let the kids feel more like they're in their classroom. So the kids are in this EEG lab, and now let's talk what's happened inside, or what was exactly the thing that we asked them to do. Okay, so together with Shelly, we created this nice task where the kids sitting in the room and they're listening to their teacher teach them something new about famous photographers. And the reason that we chose famous photographer is because this was part of the curriculum of this year for these kids. So it was actually relevant to what they did in the social study classroom. And you can see here part of the task that the teacher told them. Now I want you to imagine being this kid. You just came from your classroom to this experiment. You are sitting in a school-based lab. You are listening to your teacher. All the stimuli was recorded by the teacher. So you are listening to her natural voice in her own language, a voice that you are familiar with. It's your teacher. And you are trying to learn something that is relevant to to the thing that you're already familiar from your classroom. And we asked the kid to listen to the teacher, and we told them that we're also going to ask them some questions, so they need to really listen to her. But again, trying to put more naturalistic scenarios into the lab, we try to create something that is more related to the life in the classroom. And because we are focusing on attention, we added a little bit competition to this design. And while the kids needed to listen to their teacher, there was also all kind of visual images on the screen in front of them. All of them was about different photographer that are not related to what they just hearing from their teacher. And we try to create a scenario where the kids try to listen to the teacher, but there is something in front of them, like a worksheet, or they are looking at a book that it might be related, it might be a little bit not. And both of the auditory and the stimuli and the visual stimuli were presented simultaneously all the time. And the kids, we had two conditions in this task. The first condition was the active listening. So the kids are in the room, they're listening to the teacher through, by the way, we did not use any headphone, it was through loudspeaker. They're sitting in the room and they need to listen to the teacher. We ask them to keep their eyes on the screen, but ignore all the visual images. The second condition was the passive listening. So this time we asked the kid to do a visual task. And because the auditory and the visual stimuli presented simultaneously all the time, the voice of the teacher is still there in the background, but the kids is now focusing on something else. And after the kids did this task, we had two behavioral measurements. And again, this was designed together with the teacher. We asked the kids to choose from 4 pictures which one of these pictures was taken by the photographer that they just learned about. One important thing that I want to mention here is that they never saw this picture before. This was not part of the visual stimuli, which means that the kids needed to really listen to what they just learned and try to induce what is the photography style of this photographer. So it's not just a memory task, it's really more about learning. The other thing is that we ask the kids to describe the photography style of the photographer in their own words. And we got all kinds of answers. Each one of these answers was coded between 0 to 3. And again, this is something that we work with the teacher about. So this is the behavioral task and the behavioral measurement that we have. And I want to tell you a little bit about how do we look at the brain. So our question, there is all kind of measurement that you can think about when you are doing this kind of audiovisual selective attention task, especially if you are working with natural stimuli. We decided to check how well do students track their teacher's speech. Depend, of course, of their attentional allocation. So the stimuli that we have is the natural continuous speech of the teacher, and specifically we took the acoustic envelope, the acoustic feature of the speech. And the response that we have is the neural activity, right? This is how the brain interprets the speech, and this is the signal that we have from the EEG net. And the measurement that we are doing is a computational model called temporal response function. I'm not going to go into the mathematics behind it. I can talk about it later, but you can think about this function as a filter or a convolution function that help us understand what are the most important temporal windows that the brain need when it's encoding the speech. And for the scope of this lecture, you can think about this like an ERP wave. The bigger the peak, it means that this time is more significant and that something interesting is happening in the brain. And after all of this intro, let's talk about the results. All right, so our question, is how does directing auditory attention to your teacher influence speech processing in complex learning environment? And this is what we are seeing. So this is a TRF function, and again, you can think about it like an ERP. For the scope of this presentation, the x-axis is the time or the temporal leg of the model, and the y-axis is the weights of the model. On red, you can see the active condition where we ask the kids to pay attention to their teacher and listen very carefully to what she's saying. On the blue line, you can see the passive where the teacher was still talking, but we asked the kids to do something else. And in this TRF, we can see two important peaks. The first peak is the early processing. And you can think about that like hearing. So the brain understands that something happened in the world. There is no further processing, but the brain understands that something happened. And you can see here that there is no difference between the condition. So no matter where your attention is, when the teacher is speaking, you understand that something is happening. The second peak is a more late peak that relates to more higher level processes, relates more to attentional ability, executive function. You can see from the topography that the core is frontal regions. And here we see something very interesting. We see that there is a difference between the active and the passive condition, which show us that when we are allocate our auditory attention to the teacher, and again, this is a very rich and complex and natural design, when we are putting our attention in this scenario toward the teacher, it enhances late-stage speech processing. And for us, this was a great proof of concept. There are other studies in the literature that showing that attention can enhance late-stage processes of speech processing. But we did work with very natural and controlled speech. We work with kids. So it was a great thing to see that we can really replicate other studies in the literature. And this is interesting by itself, but taking you back to the bridge that we are building, let's connect these results to what's really happening in the classroom. And for that, we went back to the teacher. We gave her all the name of the kids that were part of the experiment, and we asked her to rate these kids based on what she's seeing in the classroom. So now we have a long line of kids, and it was interesting because it took her 20 seconds to do it. Just show us how well she's familiar with the kids. And she rated all the kids based on their attentional profile from high attention profile, which is kids that she predicts that they will have high chance of succeeding the task based on their class behavior, to kids that have low attention profile, kids that she's predicting that they have a low chance of succeeding the task based on their class behavior. And this is something that only the teacher could tell us, because in the lab, in the room, sitting with the kids, they act very differently from what they really act in the classroom. And I know because I did class observation and I watched the same kids inside and outside of the lab. And then we also asked the teacher what were the parameters that she was thinking about when she did this rating. And this was really interesting because I'm going to show you some of the things that she mentioned. She was talking about body language in the classroom. She was talking about the kids' ability to process instruction, their memories ability and recalls abilities, and how motivated they are to learn and do well. So this is just like an example. I don't have really quantitative data around it, but for me, that was kind of the point where I understand why is it so important to work with teachers, because if none of these parameters have the word attention within it. And the way the teacher and I was talking about attention, was talking about attention in the class was so different, which was another kind of improvement for me to say, okay, it was so good to work with each other. It was so important for me. And all of these parameters or her approach was another piece of the puzzle to better understand how attention is operated. So now going back to the rating, we have two groups, right? One group is kids that the teachers say that they have high attention profile in the classroom. The other group have low attention profile in the classroom. And I want to go with you over the TRF of each one of this group. So here is the graph, the figure of the kids with the high attention profile. Going to do it slow, step by step. What we're seeing here is again the two peaks, the early and the late one, for the active and the passive condition. And here we can see a beautiful difference in the late processing neural response, suggesting that these kids are very good at shifting their attention. When we ask them to pay attention to their teacher, they are all locked in. They are processing what the teacher is saying. Their brain is able to track the teacher's speech in an amazing way. But also, from the other hand, when we ask them to do something else, when we ask them to pay attention to the visual, they can filter out the speech completely. And you can see here that in the blue line, there is no late peak, which tells us that when the kids did a visual task, they were all locked in. They moved their attention from the teacher to the other thing and did only that. And now let's see what's happening in the low attention profile group. And here we see a very different picture. So we still have the two peaks, meaning that in this group of kids, we still have the early and the late processing. At this time, there is no difference between the active and the passive, which tell us that these kids, when they are trying to listen to the teacher, they are kind of doing both things simultaneously. They're a little bit listening to the teacher. Their mind might be wandered to something else. Their attention is divided between the stimuli. And this is happening when we ask them to pay attention to the teacher and when we ask them to do something else. They are doing a little bit of both. And if we are going back to the second slide that I show you, and we're thinking again about the superpower and the way kids can control their attention, what we're seeing is that the student that classifies high attentional profile show better ability to control and shift their attention. And because this division was based on classroom observation about the deep knowledge that the teacher have with these kids, this can give us the first stepping stone to think about neural mechanisms that help kids in their school, that help kids to be better learner. So, summary. We co-developed an authentic classroom learning paradigm together with teacher. We showed that auditory attention enhanced late-stage speech processing in natural learning environment. And we showed that students with stronger classroom attentional profiles show better control on their attention inside of the lab. Going back to the goal of this study, we can check the first goal to develop something that it is relevant and meaningful to learning in the classroom. And the second one, which was about identified possible neural mechanism that can help us understand attention in real life. But the third goal is still open because the important thing for me in this work was to show or to examine if we can take all these lab-based attentional dynamics and connect it back to the classroom. And with that, let's talk about the second study. So the second study is from the lab to the class, the other direction. The goal was to characterize how lab-based attentional patterns manifest in authentic learning environments. And a good time to say thank you to my amazing research coordinator, Voni and Ander, because it takes a village to go outside and take neural measurement from kids inside of a school. And I was so lucky to work with both of them to make this study happen. And in addition to the people, this is a good time to tell you a little bit about the device that we used. So you can see here, this is me putting a VR 300 device on one of our kids' head inside of their classroom. The VR 300 headset are 7-channel system. We have 6 channel in the back, occipital and occipoparietal, and we have one sensor which is equivalent to FC in the front. These are all dry electrodes, which mean that we have no gel, which is something that I wasn't thinking about, that it's so important before I work with teenagers. But for teenagers, it's very important to work with a system without gel that's going to mess their hair. We had a very easy implementation of this. My personal record is 5 minutes between putting the helmet on, do all the adjustment, and get a good quality signal. And the most important thing for me is that during the entire process, kids were super excited to try it on and to work with the helmet. We did a lot of work, and I'd be happy to talk about it if someone is going to do more studies inside of schools. We did a lot of work with the kids to make sure that they have enough exposure to the helmet and that the helmet is part of their school life. So we went to classroom, we work with kids, and no matter which was the classroom or even the age group that we work with, when we put the helmet on and we ask which one of the kids want to try it on, all the kids raised their hand, which was really excited. I'm not going to talk about the specific signal quality. We have the wearable sensing people here to question about that, but I do invite you, if it's interesting for you, to go to a paper that I published this year that compare this system to other mobile EEG system in the scope of precision individual level EEG. All right. So we know what we're looking for. We have the device, we have the kids that are super excited of us coming to their classroom. And one last thing that I want to mention is that in this study, we work not with one, but with 4 teachers to design the classes, to design the environment. We work with social study teachers, STEAM, language art, and math. We wanted to make sure that all the classes that we are working at are kind of similar in terms of the environment. Kids are sitting next to a table, listening to their teacher. But we did a lot of work to make sure that all the classes are kind of similar, even though they're teaching the kids different stuff. And you can see here all our participants with the helmets on their head. We had 32. We had 32 participants, 5th and 6th grade student. We work with 2 kids every time because we had 2 devices. So we had 16 sessions overall. All of the kids are the same kids, the same cohort at study 1. And again, going back to the bridge from the lab to the class and back, each student was measured once, and we had around 20 minutes of neural recording per class. But in addition to the neural measurement, because we are already in the classroom, we are already inside of the school, we wanted to make sure that all the kids in the classroom would feel included. So we have 30 something kids that had the devices on their head, 2 kids in every class. But in addition to the neural measurement, 5 time points per class, we stopped the class, and this was again coordinated with the teacher, and we asked the kids to rate the level of their attention and the direction of their attention, whether it's more internal or external. And this is a very subjective measurement. So we also had an objective measurement, which is a recall question. Again, designed with teacher. We ask the kids question that is related to the content that they just learned in the class. So we have neural measurement from part of the student, and we have behavioral measurement from all the students, all the 5th and 6th grade students at Synapse School. This means that we have around 60 something samples. And this is how each one of our classes look like. We had a 45 minutes class. 5 to 10 minutes after the class was started, we started our EEG recording. And you can see that this was around 20 minutes of recording. In addition, we have 5 time points where we ask the kids to rate their attention. And in the middle of the class, we also ask the kids a recall task. So you got all the technical information about this study, but I also want to show you how it's really look like because it's really cool, I think. And you can see here one real session. This is a math class. You can see the teacher with the heart on her face. She's talking with the kids. I think it was about a mathematical operation. But in the yellow circle, and this is the more important part, you can see the kids here. We had two kids sitting with the mobile EEG on their head. They are sitting in the back of the class. This is also something that we coordinate with the kids to make sure that they will feel comfortable and will not draw a lot of attention from their peers. Behind of these kids, you can see me and Ander with our laptops tracking the signal, make sure that everything is fine. And you can also see Vonnie standing next to the table, and she was our observer. She decoded everything that happened in the classroom on real time, minute by minute. And the last thing that I want to show you is the small attentional packets. And you can see, I hope that you can see that there is like a paper packets and a paper in front of each one of our students. And this is where they rate their attention and answer the recall question. So this is the scenario, this is the environment. And now let's talk a little bit about the results. So starting with the behavioral results, what you are seeing here is our attentional level correlated with recall score. And the recall score is again the question that we ask the kids. And here you can see a positive correlation, which was another proof of concept showing that when the attention is high, kids are answering on the recall question in a better way, more rich answer. The answer are more relevant. And this was a nice thing to see and kind of ensure us that although this is a subjective measure, it is still relevant to their learning outcomes. The other measurement that I want to show you is how the teacher ratings from the first study correlate with what we are really seeing in the classroom. So if you remember, we asked the teacher to rate the kids based on what she's seeing in the classroom. And now we wanted to see if her rating is really relevant to what's happening in the classroom, and if it's not just something that was relevant to one class or one scenario. And what you can see here is on the y-axis, the rating of the teacher going from high to low. And on the x-axis, again, the mean recall score. And it was, again, significant correlation showing us that kids that the teacher predict that they will succeed in study one will actually show better learning outcome, better learner in the classroom. And again, this is not just a social studies class. This is a mean, each point here is a student and the mean score of all the classes together. So the bottom line here is that the learning outcomes were shaped by both momentary attentional scoring and stable teacher-rated attentional profile, which again remind us why is it important to look at attention from different angles. And now let's talk about the brain. So how does brainwaves look at a classroom? As I mentioned, in the VR300, we have only one frontal channel, which is equivalent to FZ. This is the channel that we looked at. This was the channel that was significant in the lab, and that's why it was interesting and good for us to see how the TRF shaped through this channel. And the first thing that I'm going to show you is just the general TRF response of all the kids together, 31 kids overall. And again, I want to remind you that this neural activity was recorded from different kids in different classroom, and these are 9 to 12 years old kids. And we got a beautiful TRF response, which maybe for some of you look like a gray figure, but for me, it was one of the most exciting things that I saw in my entire academic career, because it showed me that I was able to capture reliable and meaningful neural signal that relate to speech processing from kids, from classroom. And as I mentioned, when I talked about natural environment, this is not obvious at all. And what we're seeing here, although this wave is a little bit different from the one that I show you in the lab, it is still significant, it is still meaningful, and give us kind of a green light to go to the next step, which is talking again about the attentional profile. So we have two groups in front of us, and these are the same group from study one. We have the high attention profile, we have the low attention profile. This is what we saw in the lab. Now let's talk about what we are seeing in the classroom. And in the green, you can see the high, on the purple, you can see the low, and you can see two TRF waves, very similar to what we saw in the classroom, that they got early peak and late peak, where in the early peak, there was no difference between the group. But when we look at the late processing, when we're looking at how the brain is processing a high level feature of the speech, we can see a difference between the group. We see that the kids with high attentional profile got the second peak, which was missing in the second group. And the last thing that I'm going to show you today, and I know it was like a lot of results, but there was one last important thing that I want to show you that relates to natural measurement and TRF. And this is predictive power. So when we are creating a computational model, one of our measurement to assess the quality of the model is to measure how accurate does the model predict neural responses, or what is the correlation between the predicted and the observed signals. And this is an R Pearson or Pearson correlation. And you can see here again the two groups, the high and the low one. And what we saw is that only the group with the high attentional profile shows significant predictive power above chance, which is indicating that their ability to track the teacher's speech was more efficient or at least different from the other group, which was very, very interesting when we are trying to do this translation from the lab to the class, the fact that our results mirroring what we saw in the lab. And so that study one and study two connected together. And with that, I'm going to go back to the goal of the study. And we kind of checked all the goals that we created translational paradigm. We identified neural mechanism, but we also were able, using this bridge, using this research practice partnership, to link the lab-based results to what we are seeing in the classroom. And if I want to summary everything together, we built a lab to classroom bridge, a framework for uncovering attentional mechanism across context. We did it together with teacher. I showed you that students' neural attentional patterns in the lab differed based on their classroom behavior. And I also show you that in the class, we are seeing similar stuff, and the neural dynamic kind of mirrored the lab-based attentional effect that we measure. And for me, the most important thing, more than just look at each stage by itself, is now to start and observe the interaction and see if the patterns that we're seeing in the lab can help us better understand what is happening in the classroom, which is something that I wouldn't be able to do if I was looking at each one of the contexts by itself. Okay, so exciting by itself. Now let's talk about what's next. For me, it was a great first step. Just gave me another insurance that we need to advance externally valid studies that grounded into mechanistic lab-based paradigm. Going into the real world is exciting, it's cool, but we also need to make sure that we understand what exactly we're studying. I encourage you to do it together with practitioner, educators, students, and people that are relevant to your field of study. My next step is to scale it up. And this was a study that I did with 30 kids. I want to do it with more kids to see how this pattern diverges between different cohorts. And maybe in the future, this will help us to develop more personalized attention support intervention, try to identify what is the superpower that each one of our kids have and how we can help them use it better. And with that, I'm just going to say thank you to all the people that helped me in this study, a lot of people. And I also want to leave you with some of the reflection of our student. For me, it was very important to share the science with the teacher, with the student. So we also came back to them with each phase of the experiment and explain them the science and ask them what they think about it. So you can see all kinds of funny wonders. The one I love the most is why is it so boring to be in a lecture, which I hope wasn't the case for you today. And with that, I'm going to finish and open the stage to question. So thank you, everyone.
Amazing. Thank you so much, Adi, for the wonderful presentation. Thanks for sharing all these insights from your research. This is really, it's such an interesting project, and it's really great to see how excited the kids were to be participating and also wearing the devices. It's very cool. All right, great. So we have a lot of questions here in the Q&A.
Mhm.
We'll try to get through all of them. But the first question is, how do you know if the peaks are time locked to a specific stimulus in a naturalistic setting? The two peaks, are there any way to verify their interpretation?
Oh, so this is a great question. So I want to say something about TRF in general. The stimuli that we are working with here is it's not event related, it's not a specific event in time, it's the natural speech of the teacher. What we are doing is that we are extracting the acoustic feature of the speech. Each one of our teacher got their own recorder on her. So we have the speech in real time and we're able to extract the speech, extract the envelope, and then synchronize it with the neural activity. Specifically, and I'm sorry for being a little bit technical here, I work with lab streaming layer, which is an external feature that kind of synchronize different stream on time. Um, I specifically have a lot of experience with mobile EEG devices, so I'm also very concerned about timing and synchronization. Um, I'd be happy to talk more about it if someone is thinking about this stuff. It's tricky, but we did a lot of validation to make sure that we are recording what we are thinking we are recording.
Great. Thanks so much. The next question comes from Walid. He's asking, how do you distinguish if the kid is attending to the picture or to an audio? Is there any additional data besides the instructions, for example, maybe eye tracking?
Great question. No, we don't. We didn't do eye tracking, and we wanted to do. We had all kind of things that are relevant to the kids' privacy in terms of putting camera in front of them. This is one of the things that in hindsight I would have done, like adding eye tracking can benefit a lot of the design. There are all kind of research group, by the way, that try to combine eye tracking and EEG. I think it's important, and I wish we had it, but we didn't. What we did had, and inside of the lab, we had one team member from the research team that sat in front of the kids and make sure that their eyes gaze is toward the screen. If the kids shift their eyes, we remind them during the break to look at the screen directly. We also ask the kids, about it. And we all kind of like reminding that they need to learn by looking right now or learn by listening. But I agree that it would be better if we had eye tracker.
Great. Yeah, that makes a lot of sense. Thank you. Awesome. Well, the next question is, how do you define the 0 ms or milliseconds for the TRF?
Right. So TRF is more, and for those of you who want to learn more about it, I really love this method. Please feel free to send me an email. I can send you some paper about it. But we can think about TRF as a convolution. So zero is actually the zero time lag between the stimuli and the response. It's not really zero in real life because it is a continuous stimuli, but it can show us the best temporal window that show the best fit between the stimuli and the response. And this is kind of what built this computational model. So I hope
Great.
it's answer, and if not, feel free to approach me and I'll be happy to share some materials about it.
Sounds great. Thanks, Adi. Yeah, a lot of questions coming in here. Another question is, did you include any participants with attentional deficits like ADHD? And if
Yeah.
so, did you observe any differences in their neural responses?
So this is a great question. I can show you one slide that might help with that. So what you can see here is the cohort of our kids. These are 32 kids that we measure, 39 kids that we measure in study one. We had in what was important for me, I will start maybe with that. For me, if we are in school, it gives us the opportunity to give every kid opportunity to participate. So we didn't have any excluded criteria. We, of course, had all the demographic and medical information of the kids, but each one of our kids, they say, I want to be part of the study, was part of this study. From a group of 40 kids, we had 5 kids with ADHD. All of the kids did the experiment with medication. And you can see here 2 axes. One of them is the teacher ratings of the kids. And you can see that we have 1 kids with ADHD. These are, by the way, the red dots that were part of the high attention group, 4 kids in the low attention group. And one of the things that we also took is a measure called ASRS. This is a questionnaire that the kids filled about their own attention. And you can see that it's also somewhat correlated with the ADHD, diagnosed ADHD. So we have this prediction. We don't have enough kids to say something real about kids with ADHD, especially because these are, of course, varied in the neural activity between each other. And this is one of my goals of scaling it up. Try to see how it looked like if we're looking at the entire cohort of kids with ADHD and maybe without ADHD and see if we see any differences there. I
Awesome.
don't know
That's
if
really
it answered the
interesting. Thank
question,
you.
but sure.
Great. Well, we have one more question, or I'm sorry, we have several more questions here. Similar to the last question, did the two studies reveal any differences in gender?
I didn't look at it. So I don't know. It's interesting to check it. I don't know.
I see. Great. We have another question from Maria. She says, "Thank you very much for your presentation. It was very interesting." She has a question about study one in particular from the
Mm-hmm,
class of the lab.
mm-hmm,
In the image you provided as an example, the participant is holding a toy.
mm-hmm.
Is this
Yeah.
something that's recommended during measurement? Do you think that this affects learning by acting as maybe a bit of a distraction? And then she's added some context here. She asked because she's taught in a laboratory, a class setting, and then she's mentioning there maybe shouldn't be any distractions between the participant and the screen. So she's just curious if that had any effect.
Okay, so first of all, I'll be happy to talk more about it. Some phrasing about the this boba plushie. The boba was one name that we gave to other part of the experiment. This was a name that we gave together with the kids. It's an acronym to think that the kids needed to do. So this is why we have the plushie as kind of our mascot for this experiment. But when we work with the kids in the lab, one of the things that we saw that it's helped the kids to have something in the break that they can play with and kind of taking out all their fidgeting behavior. So this plushie was not with them during the experiment, but during the break we gave it to them, and they were squeeze it a little bit, and they moved their hands and they moved their feet before getting to the next block of the design. And this kind of helped them to sit more still and to be more concentrated in the experiment. So
Great.
things
That
that
makes
you learn when you work with kids that I never needed to do before when I work with adults.
Yeah, very interesting. Awesome. Well, the next question we have is from Yehuda, and
Mhm.
they ask, the environment was controlled with visual and auditory parameters, but have you addressed anything like mood or temperature or odor?
We did ask the kids after the block. The full design of the experiment in study one, we have 6 separate blocks. In each block, they learn about different photographer. After each block, we ask the kids about their level of attention. We also ask them about the level of interest. As part of our letting the kids feel more comfortable, we ask them about how the day was and if there was anything interesting during the day. But I don't think that we decode this information. I have it, but I don't think we decoded it. So this is very interesting to check. I do want to say something about the benefit of working in a center that is inside of a school. The BLC team know all the kids by heart, and there was not one I can think about like 3 sessions where we came to pick up the kids to the experiment from their classes, and the kids say that they are stressed about an assignment or they want to stay with their friend. And we say, okay, then let's not do the session today. Let's take a different kid. And this is kind of the advantage of working in a flexible environment that you can just work with different kids simultaneously. So we did take it into account. We did not decode it, but it is interesting. Thank you.
Awesome. Very interesting. Thanks, Adi. I think we have time for a couple more questions. Let's see. Yeah, this is a great question. Jeremy asked, do you imagine, or how do you imagine that these findings and maybe the methodology you used would translate over to adult learners?
Wow. Um, Great question. Um, I don't know. The answer is that I don't know. I can imagine there is not a lot of studies about adolescence in general. This group is kind of like a lot of studies on babies and young kids, a lot of studies on adults, adolescents. It's kind of a bit of a black box. Um, I don't know. I think that this would be something really interesting to see. One of the things that I also want to do as my future direction is to do more longitudinal studies. So if I am working inside of a school, I'd be able to do this kind of experiment of young kids toward adolescence, and maybe do a control group of adults. But I don't know. I can imagine maybe similar patterns in terms of the control of their attention, but working with adults, it's really hard to get measurement on their natural learning environment, right? Because I don't have a teacher that can say something about them.
Right. That makes a lot of sense. Great. Well, with the last few minutes here, I think we've probably just got time for one more question before we do maybe closing remarks. And I think this is a really great question. Somebody asks, how do you envision this research influencing educational practices in the future?
Yeah, great question. The number one question that I get from every teacher that I work with, showing the result, and teacher are like, okay, but how is it going to help me? So we know that in the future, I think for me, I'm from the beginning of my way in neuroeducation, I always find myself thinking what are the added value of neuroscience to the class? How can we use our measurement to say something new the teacher not already know about the kids? And for me, there are two answers. One is that these results help us to do better identification of individual learner. For example, sorry, I'm going to bring it to this slide. Um, Imagine that we have kids that their neural profile is similar to the one in the low attentional group. Now we can see if we are doing work with these kids, if we are teaching them all kind of attentional related practices, can we bring them more toward a high attentional kid profile? And if so, then we have kind of verification that all the things that we did, we actually succeed. As the other thing that we have is a more um, objective measurement of progress and neural activity that is more of what we currently have in the field of attention. Right now, the measurement that we have when we try to diagnose attention or think about attention individual student are questionnaire and teacher evaluation and sometimes the score of the kids in the test. And these measurements are not fully capture attentional profile. They're not fully capture the kids. They're doing kind of a redundant to a very specific point of view, a very specific score. So I hope that this line of study can help us better understand each one of our kids individually.
Amazing. I love that. Yeah, that's great. Awesome. Well, thank you so much. I would love to keep going. We've got many more questions, but we're unfortunately we're right at our time for today. So I want to first say thank you so much, Adi, for your time
Sure.
today and for giving us a bit of a deep dive into your research. We're absolutely thrilled to be supporting your work, and we can't wait to see what comes next in these real world classroom projects. So thank you again.
Amazing. Thank you. And thank you, everyone. And if anyone have question or want to discuss, feel free to approach me. I'm available in my mail. So thank you. And thank you, Wearable Sensing people, for having me.
Absolutely, yeah. Thank you, and thank you everyone again for joining us today for our first episode of Revolutionizing EEG. We hope you gained some valuable insights from Dr. Korisky's research. And if you want to learn more about these projects, we really encourage you to go check out the Stanford Educational Neuroscience Initiative website, or follow Adi or others from Stanford on LinkedIn. If you're interested in learning more about the VR300 or any of our other DSI dry EEG systems, please feel free to connect with us at wearablesensing.com. And the last thing I'll say is if you're part of our wearable sensing community and you're using DSI systems in your research, and you'd like to participate as a speaker in this series, please reach out to me at ryan@wearablesensing.com. We'd love to, we'd be happy to highlight your work in a future webinar. And with that, yeah, everybody have a great weekend. Thank you so
Yeah,
much, and we'll see you for the next episode.
thank you. Bye, everyone.
Thanks, Adi.
Bye.